In this video series, we will learn how to break vectors into their components. How to take the magnitude and direction of an overall vector and break it into components. Also, we will learn how to determine the magnitude and direction of the overall vector when you're given its components. So we will also learn how to move in this direction. When you're given the components, you need to know how to figure out the magnitude and direction of the overall vector. So these are really crucial skills for your success in your physics class. But sometimes professors and textbooks don't spend too much time on this because maybe they think it's pretty easy. But I think a lot of students don't think it's so easy. So in this video series, we want to make sure that we understand how to do both of these crucial tasks for physics: breaking vectors into components and figuring out the overall vector from the components. And we will be making heavy use of the mathematics that I covered in my video series on SOHCAHTOA. So I have a video series on sine, cosine, and tangent and SOHCAHTOA. So if you are weak on using sine and cosine and tangent, you should definitely watch that SOHCAHTOA video series before watching this one. Links to those other videos are in the video description box, and please also look at the video description box for a number of other additional resources that accompany this video series. All right, so let's look at an example here. Now, in this video, I've already been using the term vector. I hope that you're already familiar with the term vector from your physics class, but just in case, let's review that. What is a vector? How would you define a vector? By the way, when I ask questions in these videos, I hope that you'll actually come up with an answer to the question so that you're participating in the video. You should pause the video if necessary to come up with those answers. So my question was, can you define a vector? I hope you came up with an answer to that. So here's a good definition. I hope that you've already seen this definition in your class. A vector is a concept, a type of concept that has a magnitude and a direction. Now, of course, that raises the question, what is a magnitude? So let me ask you, what is a magnitude? Again, I hope that you actually came up with an answer to that question. Pausing the video if necessary to come up with an answer. What is a magnitude? Well, a magnitude is a number that can be either positive or zero, but that could never be negative. So let's apply that to these two examples. So A here is a vector. Concept A is a vector, and that's indicated by this little arrow above the symbol. An arrow above the symbol, you should know, indicates a vector. So it should have a magnitude and a direction. What is the magnitude of vector A? 5 units. It has a magnitude of 5 units. Notice that that is a positive number. And how would you describe the direction of vector A? Well, the direction is given by this angle. So we could say that the direction is pointing at an angle of 15 degrees with the horizontal. And notice that we can use this arrow to represent vector A. The direction of this arrow represents the direction of vector A at an angle of 15 degrees above the horizontal. And also the length of this arrow represents the magnitude of vector A. So we imagine that this length represents a length of 5 units, representing the magnitude. Now here we have another vector, vector B. You can see it's a vector because the symbol is written with an arrow over the letter. That's the symbol for a vector. What's the magnitude and direction of vector B? I hope you came up with answers to those questions. Well, the direction of vector B is at an angle of 15 degrees above the horizontal. So notice that vector A and vector B have the same direction. It so happens that vector A and vector B have the same direction, 15 degrees above the horizontal. Do they also have the same magnitude? Well, no. What's the magnitude of vector B? The magnitude of vector B is 8 units. And notice that's, again, a positive number. And this arrow represents vector B. The direction of this arrow represents the direction of vector B, again, 15 degrees above the horizontal. And notice that this vector, this arrow, is longer than this arrow because this magnitude is greater than this. Remember, the length of the arrow represents the magnitude of the vector. So since vector B has a greater magnitude than vector A, this arrow should have a greater length than this arrow. Now, I probably did not draw these two arrows perfectly to scale. I probably didn't draw them perfectly to scale to represent 5 and 8 units, but I was trying to at least, we should at least make an effort to draw this arrow longer than this arrow to indicate that this vector is, has a greater magnitude than this one. Technically, what we should say is that the length of the arrow should be proportional to the magnitude. The length of the arrow should be proportional to the magnitude, although again, when you're drawing arrows freehand, you're usually not going to end up drawing them perfectly to scale. And these arrows that I drew here, again, were probably not perfectly to scale. Okay, so make sure that you're familiar with these concepts of vector and magnitude. Those are concepts, obviously, that we'll be using over and over in the rest of this video series, and that you'll be using over and over in the rest of your physics course. By the way, if you're just starting your physics course, you probably feel at this point that you probably don't have a complete understanding of what it means for something to be a vector, or why vectors are useful. That's natural. As you proceed through your course, you'll get a better understanding of what vectors are and why they're useful. And in fact, as you proceed through this video series, I hope that you'll feel that you're getting a deeper understanding of what a vector concept is and why it's useful. So your understanding starts by learning this basic definition, but your understanding will deepen, hopefully, as you go through the rest of this video series. And then deepen further as you go through the rest of your physics course. Notice that these two vectors have different magnitudes, but they have the same direction. Now, what are components? Well, the x component is a way of measuring or representing a vector relative to the x-axis. And the y component is a way of measuring or representing a vector relative to a y-axis. So we can see right from the beginning that components are meaningless unless you specify your axes. Anytime you're dealing with components, you have to have a specific set of x and y axes that you're dealing with. Okay, so what we have to do now is we have to start learning how to break vectors into components. We have to start learning how to represent any vector in terms of components. So let's start working on that. Okay, well, here's a method, or really two different methods for drawing the components of a vector. There's a right triangle method, and there's what we could call a rectangle method. Those are two closely related methods for drawing the components. Now, all these ideas will make a lot more sense with a specific example. So here's a specific example. You might want to pause the video now and see whether you can use one or both of these methods to draw the components of this vector. Okay, now let's go through that together. So the first thing that we're going to want to do here is to copy our vector. So I'll take this vector and I'll copy it, and then we can use that copy to use one of our methods. So there's two methods, the right triangle method and the rectangle method. So let's start by showing how we can use the right triangle method to draw the components of this vector. So the first thing we can do is start over here and draw a line that's parallel to the x-axis. So a line that's parallel to the x-axis, that would be a horizontal line. Then we can go here to the head of the arrow and draw a line that's parallel to the y-axis. That would be vertical in this case. And notice that the intersection forms a right triangle. So that right triangle gives us the components. This is the x component, the part that was parallel to the x-axis. And this is the y component, the part that's parallel to the y-axis. Those are supposed to be straight lines as best I can draw them. Now we have to put arrows on the components because the components are also vectors. Components of a vector are also vectors, so they have to have directions. So what are the directions of these components? Well, that's where this rule comes in. The components are supposed to represent the overall vector. So wherever the head of a wherever you the vector, wherever the component is at the head of the overall vector, you should also see the head of the component. And the tail of a component should be at the tail of the overall vector. For example, here for the y component, this is the head of the overall vector. So to represent that, I'm also going to put the head of the component here. But over here, the component overlaps with the tail of the overall vector. So I'll make that the tail and this the head. For horizontal and vertical vectors, it's maybe just easier to say that the overall vector points up and to the left, and therefore our components should point up and to the left, so that the tail of this component is on the tail of the overall vector, and the head of this component is on the head of the overall vector. By the way, I hope that you understand that this is what the tail of an arrow looks like, and this is what the head of an arrow. This is the head of a vector arrow symbol, and this is the tail. So the tails are in the same place, and the heads are in the same place. That's one way to get the components correct. Now, do you see how the components represent the overall vector? If I start here and I trace the overall vector, I'll get to here. And notice that if we trace the components, we get to the same place. If I start here and I trace the x component and then the y component, I get to the same place. That shows that the components represent the overall vector. In fact, you can see that the components add up to equal the overall vector. The overall vector is the sum of the two components. Like I said, you can see the components are vectors. So technically, you could write them in the arrow notation. You could write the components with arrow notation to show that they're vectors. But most of the time, most textbooks and professors don't do that, or not, at least they don't do it very often, and that's kind of a cumbersome notation. So I'm not going to include any arrow. I'm not going to include any arrow on these components, even though technically they're vectors too. Okay, so that's one way to break this vector into components. Here's another way. There we go. So now this time, at the tail, I'm going to draw a line that's parallel to the y-axis, a vertical line. And at the head, I'm going to draw a line that's parallel to the x-axis, a horizontal line. And now you can see we have another right triangle. And so the sides of that right triangle are the components. And you can figure out, so this would be xx, and this would be hx and hy, and you can put in the arrows. So this is the head of the overall vector, so it should also be the head of a component. And over here we have the tail of the overall vector, so this should be the tail of the component, so the head for this vector is over here. Or you could just say to yourself that the overall vector points up and to the left, so the components should point up and to the left. So this is the right triangle method for writing the components, and you can see that there's always two different right triangles you can make. You can make a right triangle below the vector, or you can make a right triangle above the vector. Which one should you do? Well, whichever one is most convenient for the problem that you're working on. And again, you can see that if you added up the two components, you would get to the same place as with the overall vector. So I hope you can see how the components represent the overall vector. Notice also that I've been assuming that you recognize this notation for the components. So if h is the overall vector, h subscript x is the x component, and h subscript y is the y component. That's the normal notation that we use for components. You should certainly always label each part of your picture. For example, this is useless. Don't draw a picture like this. Include labels. Always include labels when you're breaking things into components like we have here. Okay, so now that's the right triangle method for drawing the components. We drew right triangles where the overall vector represented the hypotenuse. And how did we find the legs of the right triangle? Well, one leg was parallel to the x-axis and one leg was drawn parallel to the y-axis. And then those two legs represented the x and y components of the vector. So it's very important to see that this is totally dependent on your axes. The way you find the legs of the right triangle is by drawing two sides that are parallel to the two axes. I'll say that again. The way we find the legs of the right triangle is by drawing two lines that are parallel to the x and y axes, and where they intersect defines the x and y components. Now there's another method that is also occasionally used called the rectangle method. So let's see how to execute that method. Now the other possible method is a rectangle method, where the sides of the rectangle represent the components and the diagonal of the rectangle represents the overall vector. So let's try that method. And again, we'll base that off of this vector. So let's copy that. Now I'm going to draw a rectangle where the overall vector is the diagonal of the rectangle. The components are the sides, and also the components should be parallel to the axes. The sides of the rectangle are parallel to the axes. So over here I want to draw two sides parallel to the two axes. So I'm going to draw a line here that's parallel to the y-axis, and I'll draw a line here. These are all supposed to be straight horizontal and vertical lines. It's just tough to draw that with my drawing tablet, but that should be a line parallel to the x-axis. And then through the head of the arrow, I'm going to draw another line parallel to the y-axis, and a line here parallel to the x-axis. So notice all these dashed lines came from drawing things that are parallel to the axes. The components are based on the axes. All right, and then we draw the two components using this. You can see we formed a rectangle. So this is a rectangle method, and the two sides of the rectangle that we usually use here are the sides that are at the tail of the overall vector. So here's one of the sides of the rectangle at the tail of the overall vector. This is supposed to be a straight horizontal line, and that would be the x component. And here's another side here at the tail. So this is supposed to be the y component. And how about the arrows? Well, this is the tail of the overall vector. So where it overlaps, this should be the tail of a component and the tail of a component. So the heads of the components are over here and over here. Or you could simply say that the overall vector points left and up. So the components, to represent that, should point left and up. Okay, so this is a rectangle method rather than a right triangle method. And how do we find the sides of the rectangle? The sides of the rectangle are parallel to the x and y axes. And then the x component would be this side of the rectangle, and the y component would be this side. We usually use the two sides here that are at the tail of the overall vector. You can see this is very closely related to the right triangle method. In fact, in a sense, what we did here is we drew both right triangles. We drew the right triangle below the vector and the right triangle above the vector. And we used this side from the upper right triangle as the y component, and this side from the lower right triangle as the x component. They're just really different ways of thinking of the same thing. Notice that in all these cases, the reference lines come from things that are parallel to the axes. Of course, now you could erase this extra bit over here. Those were just drawn in there to help us find the components. The solid lines here are the components. Okay, so that's our rectangle method. So we have a right triangle method and a rectangle method for drawing the components. The sides of the rectangle are lines parallel to the x and y axes. The overall vector is the diagonal of the rectangle. And the two sides of the rectangle at the tail of the overall vector represent the x and y components. And again, we use this general rule for figuring out where the arrows on the components go. By the way, the first time I recorded this video, I described this rectangle method with a somewhat different language. I didn't really actually call it the rectangle method. And then it occurred to me this is a better way to describe it. So I'm going back and re-recording this small part of the video. So you shouldn't be surprised. You shouldn't be surprised if you watch the rest of the video if you still see some older remnants of that previous recording with a previous description of this method that I think, but I think what I have here now is probably the simplest way to think about this method using the idea that you're drawing a rectangle. All right, so we've learned the right triangle method and the rectangle method for drawing components. Which method is best? Well, basically you should just use whichever is most convenient for the problem that you're working on. I think most of the time it'll be most convenient to use a right triangle method. And which right triangle do you draw? Well, you usually try to draw a right triangle that includes an angle that happens to be mentioned in the problem. But it's still good to know about the rectangle method because you might occasionally see this used in the textbook or by your professor. Again, notice components only make sense compared to axes. So you have to write down what axes you're using in order to figure out how to draw the components. In all these cases, the reference lines for the components came by drawing lines that were parallel to the x and y axes. So there's a very close relationship between the axes and the components. Also, we learned here the right notation for dealing with components. We usually use x and y subscripts to deal with the components. And remember, always label all your arrows. So for example, this picture, or this picture, these are now useless pictures because there's no labels on the arrows. Arrows without labels are useless. Always use the notation we've been talking about to put a label on each arrow. All right, please pause the video and try this problem. And in fact, I would suggest, why don't you try drawing the components all three ways, just for practice. Our goal here is to get very comfortable with drawing the components, so why don't you use all three methods for drawing the components. So the basic approach here is that we can draw a line here that's parallel to the y-axis and another line here that's parallel to the x-axis, and here we could draw a line that's parallel to the y-axis and here a line that's parallel to the x-axis. So we could say that this is the y component. This is the x component. Those are all supposed to be straight lines. Did you remember to put in notation? Here's the notation for our x component. Here's the notation for our y component. And since here we have a tail, this should be a tail of the component. So this is the head of this component. Here's a tail, so this should be the head of this component. Did you remember to put in those arrows? That's very important. Let's see if I can draw that a little bit better. Okay, so there we go. The overall vector points up and to the right, so the components point up and to the right. Or instead, we could trace the right triangle on the top of the vector. Notice how this is a tail, so this is a tail. So I'll put the head of this vector here, and again, we should label the components. And this is the overall vector. So it's important to distinguish x component, y component, and overall vector. And again, the components point up and to the right, just like the overall vector does. Or we could use the last method that you'll see sometimes in your textbook and draw both components starting from the tail. Here's one component starting from the tail and another component starting from the tail. And again, just like the overall vector points up and to the right, the components point up and to the right. All the tails are overlapping. Don't forget to draw the components, Vx and Vy. So this represents the overall vector. Okay, so that would be three different ways that we could draw the components. We could draw a right triangle below the vector, or draw a right triangle above the vector, or we could use all these reference lines to draw the two components at the tail. Notice the key is to draw reference lines that are parallel to the axes. That's the key to drawing the components. Draw reference lines that are parallel to the axes. And where the reference lines intersect, that tells you the limits of the components. Pause the video and try this problem. Okay, well, notice that in this case, A is anti-parallel to the y-axis. And what that means is that there is no x component. So the x component here is 0, which means you can't draw it. You can't draw a 0 vector. So the x component is 0, and there's no way to draw it. And that means that the overall vector also represents the y component. So I'll say that that same vector that also represents the y component. By the way, something I'm taking for granted that you understand is that the only thing that matters about a vector is its length and its direction. It doesn't matter where the vector starts and stops. For example, these two vectors are the same. Even though this one starts and stops in a different place, they're the same because they have the same direction and the same magnitude. Still the same, still the same. It doesn't matter where you put the vector on your page or where it starts and stops. All that matters for a vector is its magnitude and its direction. So this vector is the same as this one because they have the same magnitude and direction. So my point is that when a vector is parallel or anti-parallel to an axis, when the vector is parallel or anti-parallel to the y-axis, then the y component is the same as the overall vector, and the x component is just 0. And hopefully you can figure out how a similar pattern would work if we had a vector that was parallel or anti-parallel to the x-axis. Okay, so notice that in this case we don't use this same reference line method. We don't use the right triangle method. So if you tried to write a right triangle in this case, you might have gotten confused. We don't need reference lines. We don't need a right triangle. It's much simpler. When a vector is already parallel or anti-parallel to an axis, it's much simpler to find and draw the components. One component is 0, and the other component is the same as the overall vector. Please pause the video and try this problem. Now, it might have seemed like this was the same problem as before, because we have the same vector, but did you notice we changed the axes? And if you change the axes, you completely change the components, right? So this is not the same answer as before. Now we have to do this problem all over again. By the way, I don't know if you realized, but even though most axes are horizontal and vertical in physics, not all are. You definitely can see some axes that are at a diagonal. So you definitely will see in your physics course, you will see axes that are at a diagonal. If you haven't seen it yet, you will see it pretty soon. So you need to know how to deal with diagonal axes, like this. So let's see how we'll deal with this. By the way, one place this will be important is when you learn how to do inclined planed problems, which will come up not too far in the future in your class. All right, so how do we deal with these diagonal axes? Well, this is where the systematic method that I was describing earlier, I think, comes in handy. The key is, remember, draw reference lines that are parallel to the axes. Draw reference lines that are parallel to the axes. So, for example, over here, I'll draw a reference line that I'll try to make parallel to the x-axis. I won't get it to be perfect, I'm sure, but you'll get the basic idea. All right, and maybe I'll also draw, and then over here I can draw a reference line that's parallel to the y-axis. And now you can see we have a right triangle. We could use that right triangle as the components. Or if you wanted to, you could draw the reference line here that's parallel to the y-axis. And you could draw the reference line here that's parallel to the x-axis. How did I know how to draw these lines? Well, I tried to draw these reference lines so they're parallel to the x-axis, and these so they're parallel to the y-axis. And I hope you can see now we have two right triangles we could use. We could use the right triangle to the left of the overall vector or to the right of the overall vector. So we could say, use this right triangle and say, here's a component and here's a component. Now, how do you draw the arrows? Well, remember that since this is a tail of the overall vector, it should also be the tail of the component, which means the head of the component is over here. And since this is the head of the overall vector, it should also represent the head of a component. It's a little bit difficult to draw two arrowheads at the same place because they kind of overlap, but this will be another head of a component, and that would be the y component. Remember to always label the components. Or instead, we could trace the right triangle on this side. Since this is the tail of the overall vector, it should be the tail of the component. So this is the head of that y component. How do I know this is the y component? Because this line is parallel to my y-axis. And since this is the head of the overall vector, it should be the head of the component. How do I know that this is the x component? Because it's parallel to the x-axis. All right. So notice that the head of the component should be at the head of the overall vector, and the tail of the component should be at the tail of the overall vector. Notice that doesn't mean that the tail of the component is at the tail of the other component. Here we have a component head and a component tail, but what I'm saying is that the head of the component should be at the head of the overall vector, and the tail of the component should be at the tail of the overall vector. That's what we said here. Head of the component at the head of the overall vector, and tail of the component at the tail of the overall vector. That's the general method for figuring out the directions. And one more way you could do this is to draw both components at the tail of the overall vector. Draw both components at the tail of the overall vector. Those are supposed to be straight lines, so these would all be tails overlapping. So this would be the head of one component, the head of the x component, and here would be the y component. Okay, so you can use any of these methods to break the vector into components. For most problems, one of these methods would probably be most convenient, but you might see any of these used in your textbook. So if you compare these two examples, this gives us an important lesson. Notice in both cases we have the same vector A. Here's vector A and here's vector A, but the components were very different because we changed the axes. So you can see components are meaningless unless you know what your axes are. Components are a way of representing a vector relative to the axes. So here were the components with the horizontal and vertical axes. But with these diagonal axes, we had very different components. So you can see before you figure out the components, you always have to decide what your axes are. Always you have to show the axes before you figure out the components. And again, most of the time in the class you'll use horizontal and vertical axes, but not always. There are some important types of problems where you'll need diagonal axes like this. This is the case where I think it's especially helpful to have this method of drawing reference lines. How do you find the reference lines? Well, the reference lines should be parallel to the two axes. All these reference lines that I drew were parallel to the x and the y axes. That's how we found them. Notice again how the components represent the overall vector. For example, if you start here and you trace the overall vector, you get here. Well, if you start here and you trace the components, you get to the same place as with the overall vector. That shows how the components represent the overall vector, and that gives you another way to understand how to figure out the arrows on the components. Again, you can see that the components really add up to the overall vector. Okay, so I hope you feel now that you're confident that you can draw the components. But we don't have to just draw the components, we need to get numerical values for the components. We need numerical values for the components, because those are the numbers we're usually going to plug into our equations. To solve problems in physics, we need to plug numbers into equations, and the numbers we usually plug in are the numerical values for the components. Or if we want to add the vectors, we saw we need to add the components, and the way to do that is to add their numerical values. So what is the numerical value of a component. So every component has two parts. It has a plus or a minus sign, which represents the direction of the component, and it has a magnitude. Remember that components are really a type of vector. Well, vectors have magnitudes and directions, so components also have magnitudes and directions. We usually represent the direction of a component with a plus or a minus sign. What is a magnitude? Do you remember the definition of magnitude we covered earlier? It's just a number that's always positive or negative. It's always positive or zero, never negative. So you should know that that's what a magnitude is. Please try this problem. I hope you gave that a shot. Well, first of all, we need to draw the components. And again, there's three different ways to do that. So we could draw the right triangle like so. So this is a downward arrow because this is the head of the overall vector. And here's the tail of this component. So here's the head of this vector. And we need to label this as Vx. And this is Vy. Well, notice that Vx is pointing to the left, which is our negative direction. So Vx has a negative sign. And Vy is pointing down, which is our negative direction. So Vy also has a negative sign. Okay, so there's our answers. The signs of the components are that they are both negative. Notice that you can't get those signs correct unless you draw the correct arrows on the components. Well, this overall vector points down and to the left, so the components point down and to the left. Of course, there's other ways that you could draw the components for this vector, but I hope you can see that whichever way you draw the component, you're always going to get the same signs. For example, if you drew the components below, you would get one component like this pointing down and one component like this pointing to the left, because the overall vector points down and to the left. So again, Vy would be negative because it points down, and Vx would be negative because it points to the left. So it doesn't matter what method you use to draw the components, you're always going to get the same signs on the components. Please pause the video and try this problem. So again, we need to draw the components. There's a few different ways you could do that. Draw one line here parallel to the x-axis and one line here parallel to the y-axis. That gives me the components. So this would be ax. This is a tail, so this should be a tail, so this should be a head. And this is the head of the overall vector, so this should be the head of the component. The overall vector points down and to the right, so the components point down and to the right. Well, down is our negative direction, but right is our positive direction. So we'll have one component that's positive and one component that's negative. When you're dealing with components, you should put a plus sign in front of positive components, just like you would put a negative sign in front of negative components, because you want to emphasize how important the sign of the component is. The sign of the component tells you the direction of the component. A positive component is just as important as a negative. Okay, so those would be the signs for these components. Something to emphasize is that the sign of the component is just as important as the magnitude, if not more important. A lot of students treat the sign of the component as an afterthought. Is just as important as the magnitude. So make sure you get the correct plus or minus sign on your components. Please try this problem. Okay, so is this the same problem as before? Well, it's the same vector, but different axes. So how do the different axes change things? Well, we can still use the same picture for the components in this case. Since the new axes are parallel to our old axes, or anti-parallel to our old axes, so the components look the same as before. And And AX is still pointing to the right, which is still our positive direction. And AY is still pointing down, but notice that now down is our positive direction. With the new axes, down is the positive direction. So now AY is positive. So that's the difference that changing the axes made. When we changed our positive direction, we changed the sign on this component. So this just goes to show you again that it's useless to try to figure out the components unless you've written down the axes that you're using. So you can compare these two examples. They were quite similar, but we changed our positive direction for the y-axis. So in both cases, the y component was down. But in this case, down was our negative direction. And in this case, down was our positive direction. So that changed the sign on the component. So the signs of the components depend on the positive directions that you choose with your axes. On these problems, I'm drawing the axes for you. But on most problems, you're going to choose the axes yourself. And it's important to write your axes down because without the axes, you can't figure out what the correct components are. Try this problem. Well, in this case, we have a horizontal vector that's parallel to the x-axis. So we should know that the y component is 0. Since this is parallel to the x-axis, the y component is 0. And the x component could be represented by the same arrow as the overall vector. So I can use the same arrow for the overall vector and the x component, and this is pointing in our positive direction. So the x component will be positive. If the x component was anti-parallel to the x-axis, the y component would still be 0, but the x component would be negative. So this is how you deal with a vector that is parallel or anti-parallel to one of the axes. You can still break it into components. You can still break a vector into components even when it's parallel or anti-parallel to one of the axes. It's just that one of the components will be 0. And it's still very important to tell whether this x component is positive or negative. In this example, it'll be positive because the overall vector points in our positive direction. Okay, so now we're ready to actually start breaking vectors into components. If you like, you can pause this video and try to break this vector into components on your own, or otherwise, now let's go through the problem together. Okay, so here's our vector. Now, first of all, we have to draw the components. So here's our axes again. So we're going to have to draw vertical and horizontal components. Now, in this case, I'm going to draw this reference line is already parallel to the x-axis, so all I have to do is draw a reference line through here parallel to the y-axis. And those give us the components. As usual, those are supposed to be straight lines. This is a tail, so this is a component tail, and here we put a component head. And this is the head of the overall vector, so here we'll put the head of the component. We should label the components. QY and QX. Now we could have drawn the right triangle above the hypotenuse, but then we wouldn't be including the angle we were given. So it made more sense to draw the right triangle below the overall vector. Notice how the overall vector always becomes the hypotenuse of the right triangle. The overall vector becomes the hypotenuse of the right triangle. And now we can do the signs of the components. This x component is pointing in our negative direction, and this y component is pointing in the positive direction. Figure out the signs before the magnitudes, otherwise you might forget the signs. Okay, and now we're going to have to use trigonometry to find the magnitudes. So we're going to use the idea of SOHCAHTOA. I'm going to assume in this video that you understand SOHCAHTOA and that you are comfortable with it. If you're not, you should watch my other video series on SOHCAHTOA. So we know that we're focusing on this angle, the 50-degree angle. This side is adjacent to the 50 degrees. This side is opposite to the 50 degrees. And this side is the hypotenuse because it's opposite to the 90-degree angle. All right, so should we use sine, cosine, or tangent here? The problem tells us that vector q has a magnitude of 17 units. So we can say that this length is a length of 17 units. That means we know the hypotenuse. So we want to use sine and cosine so we can use the information we know about the hypotenuse. Tangent won't be too helpful because it doesn't use the hypotenuse, which is the one number that we know so far. So we can say that the sine of 50 degrees is the opposite side over the hypotenuse. So, and the cosine of 50 degrees is the adjacent side over the hypotenuse, ka. So our opposite side is qy, and our hypotenuse is 17 units. Our adjacent side is qx, and again, the hypotenuse is 17 units. Now you might notice here that I used absolute value symbols around qx and qy. Why did I do that? Well, because SOHCAHTOA is about the lengths of sides in a right triangle, and lengths are always positive. So we actually we're not going to use SOHCAHTOA to actually find the complete component with a plus or a minus sign. We're only going to use SOHCAHTOA to find the magnitude of the component. And the symbol for the magnitude of the component is the component in absolute value signs. You may or may not see your professor or your textbook use absolute value signs like this because the professor might just kind of keep track in their head that they're only focusing on the magnitude here. But for a beginner, it's good to have a specific symbol to remind ourselves that when we're using SOHCAHTOA, we're just focusing on lengths. So these are going to be magnitudes. All right, so then we need to solve this for the magnitude of qy, and we're going to do that by multiplying both sides by 17. That cancels the 17. And similarly over here, we can multiply both sides by 17 to solve for the magnitude of qx. Now we can use our calculator. So qy will be 17 sine 50. And, oops, looks like I got careless here. This was supposed to be qx. 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 Qx should be 17 cosine 50. You want to check to make sure you're in degrees mode. So the magnitude of qy was here 13. I guess I'll just round that to 13, and I'll round this to 11, I guess. Magnitude of qx. All right, remember these are only the magnitudes. Now we have to find the overall components. Well, we already know that qx was negative. So we know the magnitude is 11. So the overall qx is negative 11. And the magnitude of qy is 13. And we know that component should be positive. So that'll be positive 13 units. So this is something important that I think some students don't realize. SOHCAHTOA just tells you the magnitude of the component. It's your job to figure out whether the component gets a plus or a minus sign. All right, now I can build this into our picture. This was negative 11 units, and this was positive 13 units. Okay, so now we've broken this vector into components. Can we check if this makes sense? Now, whenever you obtain a result in physics, it's always good to pause and ask, does the result make sense? Is there a way to check whether we're on the right track? So do these results make sense? Well, the first way to check that is to build those numbers back into the triangle. We built the numbers into the triangle, and then we can use these ideas. You should know that the longest side of a right triangle should be the hypotenuse. So these two numbers should have come out to be less than 17, and they did. If either of these numbers had come out to be bigger than 17, then we would know that we had made a mistake. And we can check a little bit more by using this idea. When you compare two sides of a triangle, the longer side should be opposite the bigger angle. So you should be able to see that this angle of 50 is bigger than this angle at the top of the triangle. Even if you don't calculate it exactly, you should see this angle is bigger than 45, and this should be a little less than 45. So clearly this is the bigger angle, and you can see that that bigger angle is opposite the bigger side of 13. And this angle here at the top is the smaller angle, and fortunately that is opposite the smaller side of 11. So if this number had come out to be, say, 14, if this number were 14, we would know that we had made a mistake, because then a bigger side would be opposite a smaller angle. All right, so we were able to check our results here and see that they made sense. Both of the legs of the triangle came out to be shorter than the hypotenuse, and the longer leg of 13 was opposite the greater angle. The smaller leg of 11 was opposite the smaller angle. So I encourage you to get into the habit of always trying to check your results to see if they make sense. And particularly, I encourage you to always check your vector components to see if they make sense by using these two ideas. All right, so now we can start trying to fill in our table here. And the purpose of this table is to give us practice with the concepts and notation. So we know that vector q has a magnitude of 17 units. So this symbol stands for the magnitude of q, 17 units. And the direction of q is at an angle of 50 degrees. Now this really only is meaningful if you also have the picture, because otherwise you don't know where the 50 degree is. But if we have the picture, we can just say that the direction is represented by this angle of 50 degrees in the picture. I'll say 50 degrees as shown in the picture. And then we can say that this symbol stands for the overall q. Well, the overall q has a magnitude, 17 units, and a direction. And we know that the arrow for q looks kind of like this. Now, let's emphasize this notation a little bit more. I don't think I've pointed this out yet. Notice that if we write the symbol with an arrow on top of it, that means the complete vector description of q. So this is only complete if we give both the magnitude and the direction. On the other hand, if we write the letter without the arrow, on top, that represents just the magnitude, not the direction. So this symbol is just the magnitude, not the direction, so we only wrote the magnitude here. This symbol with the arrow represents the complete vector description, which has to include both the magnitude and direction. So try to be careful about using these two symbols. By the way, this is consistent with the way these symbols will also be used in your textbook, except that instead of using an arrow, your textbook sometimes might just write the letter in boldface. So keep in mind, if you see a letter in boldface or a letter with an arrow on top, both of those mean the complete vector description of the vector, including both the magnitude and the direction. On the other hand, if you see the letter without the arrow and without the boldface, that indicates just the magnitude of the vector. That should be the same notation that's used in your textbook. One of the keys to success in physics is always trying to use the exact right symbol. And that's one of our goals in filling out these tables to get practice with using the exact right symbol. Discussing here are the symbols for the overall vector. These are the symbols for the overall vector. And next we're going to start talking about the symbols for the components. And you'll see the symbols for the components are unfortunately kind of different from the symbols for the overall vector. In some ways, the symbols for the components are kind of inconsistent with the symbols for the overall vector. So these are the symbols we used for the overall vector. And keep in mind that now we're going to see different symbols that we use to represent the vector components. Notice it's helpful to have separate notation for the magnitude and the direction. But when you use the arrow, that means both the magnitude and the direction. Now we want to do the components. Well, we figured out that Qx was negative 11. And our Qy was positive 13. So the direction of Qx was to the left, and the direction of Qy was up, left, and up. So the Qx arrow would be to the left, and the Qy arrow would be up. Qy arrow, Qx arrow. The magnitude of Qx is 11 units, and the magnitude of Qy is 13 units. And we saw why it's useful to have a separate symbol for magnitudes. One way that it's useful to have a separate symbol for magnitudes is that when you use SOHCAHTOA, all you're doing is figuring out the magnitude of the component. You're not figuring out the complete component with the sign. So that's one example of how it's useful to have a separate symbol for the magnitude of the component that's separate from the complete value for the component. Now, of course, most problems you wouldn't figure out every single one of these notations. You wouldn't normally work out every single one of these notations for a particular problem, but it's good practice for us to do a few examples like this where we work out all the different notations just so we get comfortable with all the different ways of thinking about vectors. Okay, so that's our example of how to break vectors into components. I would say the most important part of this is don't forget to get the correct signs. If you left out the negative sign on this component, you would get the problem wrong because you would plug in a positive number into your equations instead of a negative number. I encourage you to put a plus sign in front of your positive components. Why should you put a plus sign in front of positive components? Well, there's two reasons. First of all, it helps to remind you of the importance of the sign. This is an upward component. And also, if you remember to put the plus sign in front of the positive components, you're more likely to remember to put the negative sign in front of the negative components. On the other hand, we do not put plus or minus signs in front of magnitudes. Don't put plus or minus signs in front of magnitudes because those are always positive. So there's no reason to emphasize that they're positive. Okay, please pause the video and try this new problem. Okay, I hope you gave that a shot. Now, did you notice that this is really the same problem as before? Did you see this was the same as before? Because this is the same exact vector as before. Did you realize that? So, for example, obviously they have the same magnitude of 17 units. You might think the directions are different, but really these two directions are two ways of saying the same thing, right? Because if this angle is 40, doesn't that mean that this angle must be 50? If this angle is 40, this must be 50 because they add up to 90. So you can see this is the same exact vector as before. So technically you could just stop right now and say that the components should be the same as before. We should have the same exact components as when we did the previous problem. So if you noticed that and you did that, that's great. However, For practice, let's actually figure out the components. This will help us to understand components better and give us some good practice. So for practice, let's actually figure out the components now using the 40-degree angle. So if you haven't done that yet, please pause the video. And even though we already know this will give us the same answers as before, we will get better insight and get some good practice if we break this vector into components again, but this time use this angle to break it into components. Okay, I hope you tried that. Okay, so now I'm going to draw the right triangle above the overall vector because I want to include the 40-degree angle. Remember that the assignment here is to use the 40-degree angle. So I'm going to use that and draw the right triangle above the hypotenuse. The overall vector points up and to the left, so the components should point to the left and up. So the tail of this component is on the tail of the overall vector, and the head of this component is on the head of the overall vector. And this would be qx, and this would be qy. So should we do SOHCAHTOA now? Nope. First we figure out the signs. This x component is to the left, which is our negative direction, and this y component is up, which is our positive direction. Do the signs first. Okay. Now we're focusing on the 40-degree angle rather than on the 50-degree angle. And we know that the Q here still has a magnitude of 17 units. So this length is still 17 units. So again, we're not going to use tangent, we're going to use sine and cosine because those allow us to use the hypotenuse. So we have that the sine of 40 degrees is equal to the length of the opposite side over the hypotenuse, and cosine of 40 degrees is the length of the adjacent side over the hypotenuse. So our opposite side here now would be qx. I should label those. So this is the opposite side because it's opposite to the angle we're focusing on. And this is the adjacent side because it's adjacent to the angle that we're focusing on. So our opposite side here would be qx, but we're going to focus on the magnitude of qx because we're thinking about a length, and the hypotenuse will be 17. And the cosine of 40 degrees will be the adjacent side, which is the magnitude of qy over the hypotenuse, which is 17. To solve these for the variables, we'll multiply both sides by 17. So the 17s cancel. Then we can use our calculator. We have 17 sine 40 and 17 cosine 40. You can see we got the same numerical values as when we did the problem previously with 50 degrees. So sine of 40, that calculation gave us 10.9. our QY calculation gave us 13 for the magnitudes. Now we need to get the signed values with plus or minus signs, but we already worked out how to do that, so we already worked out that QX will be negative. So the signed value is 10.9. So do you see the difference between these two symbols? This is the symbol for the magnitude, which we use when we're doing SOHCAHTOA, and this is the symbol for the complete component, which includes the plus or minus sign. And then QY here will have a plus sign, as we already figured out. Remember that it's a good idea to include a plus sign in front of positive components, because that emphasizes the importance of the sign. This plus sign tells us that this component is upward pointing, and also it'll help us to remember when we need to put in the negative sign. If you always put a plus sign in front of positive components, you're more likely to remember the negative sign in front of negative components. So you probably won't see your professor include this plus sign, but it's a real good habit for a beginner to make sure they're understanding components and they're not forgetting the signs when they're not forgetting the negative signs. All right, and we can also build that into our picture here. This is plus 13, and this was negative 10.9. So now we can fill out our table. So this was going to be 17 units at an angle of 40 degrees. As shown in the picture. So our Q arrow looks somewhat like this. And the magnitude of Q was 17 units. We decided our QX was negative 10.9. In the direction, the negative sign means that was to the left. So we could represent that with a leftward arrow. And the magnitude is 10.9. And we saw how it was useful to have a separate symbol for the magnitude of QX, because that helped us to figure out the components. Again, when you see your professor or your textbook work out components, the textbook may not use, or your professor may not use, a separate symbol for the magnitude of the component when they're doing SOHCAHTOA, because they just kind of figure out, they just kind of remember the difference between the magnitude and the overall in their head, basically. But for a beginner, it's important to realize that the SOHCAHTOA portion only figures out the magnitude, and we can emphasize that by using a separate symbol here for magnitude. And then at the end, we use a separate symbol for the signed value, where we put in the sign ourselves. So the lesson here is sine, cosine, and tangent in this method doesn't tell you whether the component is positive or negative. That's something you have to figure out yourself from your picture. So our QY was plus 13 units. And the direction was up. And the magnitude was 13 units. Now, hopefully these are all the same answers that we got for the previous problem. Let's check. Oh, looks like I rounded differently here. Here I rounded off to 11. I should have done the same thing to make these comparable. All right, so I went back and changed the first problem, so it was rounded off to negative 10.9. So this is negative 10.9 now, and this is the same answer. You can see that we got the same answers in our calculations. We just rounded them differently. So what was the point of doing this problem if it was going to give you the same answer? Well, just to give us a better understanding and more practice with figuring out components. Obviously, in real life, you normally would only have to figure out the components once, but it's important to realize that every vector makes a bunch of different angles. This vector makes one angle with the horizontal of 50 degrees, but it makes a different angle with the vertical of 40 degrees. And technically, you could use either of those angles to break the vector into components. And fortunately, both of those approaches give you the same answer. Okay, now please pause the video and decide whether this statement is true or false. Well, this is clearly false because we didn't follow this policy for the problem we just did. For this problem we just did, we used sine for the x component, not for the y component. And we used cosine for the y component, not the x component. So clearly this is false. So why would I even ask this? Well, a lot of people think this is true because it's usually true. As you're working on problems, you'll see that in reality, you really do usually use cosine for the x components, and you really do usually use sine for the y components. For example, that's how it worked out when we did the same vector using the 50-degree angle. Notice that when we did the 50-degree angle, we did use the sine for the y component, and we did use the cosine for the x component, and that's the most usual pattern. So this is not always true, but it is the most usual pattern. This is not always true, but it is the most usual pattern to use cosine for x and sine for y. But that can be dangerous because then that can fool you into thinking that you should always follow that pattern. Or if you're not paying attention, you might be on autopilot and you might follow this pattern thoughtlessly without realizing that it doesn't apply to a particular problem. So you should recognize that this is the pattern we usually use for breaking things into components, but don't be on autopilot. You need to remember that there are quite a few important cases where you would use cosine for the y component and sine for the x component. The only thing that's really safe is to always work it out from scratch for each problem. It depends on what angle you're focusing on. Can you see why these two angles give us different patterns for sine and cosine? Notice that here we were looking at the angle with the horizontal. Here we focused on the angle with the horizontal. And here we were using an angle with the vertical, and that accounts for why the pattern of sine and cosine got flipped. So generally speaking, you're usually going to be working with angles with the horizontal, and in that case, you would generally use cosine for x and sine for y. But in this case, we were using the angle with the vertical, and in that case, things flip around, and you would generally use cosine for y and sine for x. Well, like I said, the safest thing is just to work it out using the triangle each time. The big lesson here is whether you use sine or cosine for each component depends on which angle you're focusing on. Since we were focusing on a different angle here, we had a different pattern of sine and cosine than we had up here. I think a lot of students don't realize that, and that's why they tend to make mistakes when they're breaking vectors into components. So how would you reword this so it's true? How could you reword this sentence so it's true? Well, here's the only thing that's always accurate. The general principle is that you always use cosine to find the component that's adjacent to the angle you're focusing on, and sine for the component that's opposite to the angle that you're focusing on. That was the one thing that was true for both the sine and the cosine for both this solution and this solution. Use cosine for the adjacent component and sine for the opposite component. And remember, who's adjacent and who's opposite depends on what angle you're focusing on. Let me just emphasize that a little bit. Notice that in this picture, the y component was adjacent because we were focusing on the 40-degree angle. But in this picture, the y component was opposite because we were focusing on this 50-degree angle. This is something I talked about in the SOHCAHTOA video. Who is opposite and who's adjacent depends on which angle you focus on. When we focus on the 50-degree angle, the x component is adjacent. But when we focus on the 40-degree angle, the x component is now opposite. So who's adjacent and who's opposite depends on the angle you focus on. You might want to put in an asterisk on the angle you're focusing on to emphasize the importance of that idea. And that's the basic reason why we used a different pattern of sine and cosine when we did this problem in the two different methods. But since if you do them both correct, you should get the same answer both ways. Okay, so the lesson here is don't be on autopilot. Don't assume that the pattern that usually works for x and y components is always going to work. This is the only thing that always works. Cosine is the adjacent component, sine is used for the opposite component. Try this problem. Okay, now we'll go through this together. Well, we can already fill out some material, information about the overall vector here. So clearly the V arrow looks like this, something like that. And the direction of V is at an angle of theta as shown. You have to have a picture to go along with this, because otherwise we don't know where the angle of theta is, whether it's with the horizontal or the vertical, say, or above the horizontal or below the horizontal. All right, now what's the magnitude of this vector? Well, actually in this case, since we're not given any numbers or any particular symbols, we're just going to treat this symbol V as the magnitude. The symbol V itself is the general symbol for the magnitude of the vector V, and we don't have any more specific numbers or symbols to use. So I'll just erase this this equal sign here, and just say we're just going to use this symbol V for the overall magnitude. And then all we could say about the vector is that it has a magnitude V at an angle theta as shown. Now to find the components, we're going to have to use our skills for breaking things into components. So remember that through this point we can draw a line that's parallel to the x-axis. In fact, it was already kind of drawn for us with this reference line. And through this point we'll draw a line that's parallel to the y-axis. It's supposed to be a vertical line. And then where they intersect, that shows the x and y components. So these are supposed to be two straight lines. One straight line for the x component, and one straight line for the y component. Now the overall vector points down and to the right. So the components point down and to the right. Another way of putting it is that since this is the tail of the overall vector, it should be the tail of a component. And since this is the head of the overall vector, it should be the head of the component. Next, we want to figure out the signs on the components. Remember to figure out the signs before the magnitudes, because otherwise you might forget the signs altogether. Well, remember these were our axes. They're supposed to be horizontal and vertical lines. So the x component is in the positive x direction, and the y component is in the negative y direction. Remember that it's a good idea for a beginner to put positive signs in front of positive components. That helps you to remember the negative sign here. Now, in order to use SOHCAHTOA, we can label that this is the hypotenuse. This is the angle we're focusing on, this theta, because that's the angle we were given. So we should say this side is the adjacent side because it's adjacent to theta, and this side is opposite because it's opposite to theta. And then in SOHCAHTOA, we'll use sine and cosine because those both use the hypotenuse, and we have a symbol for the hypotenuse, which is V. So we can say that the sine of theta is the opposite over the hypotenuse, and the cosine theta is adjacent over hypotenuse. What should I plug in for theta? Well, I'm just going to keep using the symbol theta. And what do we plug in for the opposite side? Well, that'll be Vy. But remember that here we're going to use the magnitude of Vy because this should be a length. which is by definition positive. And the hypotenuse, we're going to use this symbol v for the magnitude of this component. For the cosine, we do something similar, but here we use the magnitude of Vx, which is the adjacent side, over that hypotenuse of V. Now, of course, Vx is positive, but I'm still going to use the absolute values just to emphasize that in general, what we would use here is the magnitude of the x component, because we want something that's a length, which is something that has to be positive by definition. Now, to solve this for Vy, we need to multiply both sides by V. Then the v's cancel. All right, and now notice these are not the components, they're only the magnitudes of the components. So to find the actual component here, we use what we already know, that the component will be negative. And here's its magnitude. So notice how it's useful to have one symbol for the magnitude of Vy, which is what we figure out from SOHCAHTOA, and another symbol for the signed value with the plus or a minus. And the signed value comes from our own work up here. And similarly here, Vx, we decided is going to be positive. And remember, it's a good habit for a beginner to include the plus sign in front of positive components, because that emphasizes how the importance of the sign. This means that this is in the rightward direction, and putting in this positive sign helps us to remember the negative sign over here. All right, so those are the key things that we were trying to figure out in this problem, these components. Now we can go back and plug that into our picture. So Vx here would be, we decide, oh, I guess we might as well build it into this picture. So this will be V cosine theta, and this will be V sine theta. So plus V cosine theta minus V so this direction is right, and this direction is down. That's what the negative sign and the plus sign mean. So the Vx arrow, as we already figured out, is to the right, and the Vy arrow, as we figured out, is down. Okay, and then the magnitude here, this magnitude is V cosine theta. Magnitudes are always positive, so I'm not going to include a plus sign here. And this magnitude is V sine theta, and of course, since it's positive, we don't include the negative sign. All right, so it looks like I think we were able to figure out pretty much all the information we needed here. So what do we learn from this problem? This is what we could call a no number problem, because we weren't given any numbers for the vector, only symbols. A lot of students have trouble with these no number problems. They don't understand how to break a vector into components if you don't have numbers for it. But I hope that now you've seen the example. I hope that now you understand that you can break a vector into components even if you don't have any numbers for it. All you need is symbols for it. Given these symbols, we can say we're using theta as the symbol for the angle or direction of the overall vector. And if this is the symbol for the overall vector, then we can use V without an arrow to symbolize the magnitude. And we used those two symbols, V without the arrow and theta. We used those symbols to help us break the vector into components. Another big thing here is that I hope you tried this problem on your own first. One of the most important things to get right is this negative sign. If you got everything right except this negative sign, then you completely messed up. because remember, the direction of the component is just as important as the magnitude. Remember that one of the reasons we're doing this, maybe the main reason, is that when you're solving problems, you need to plug the components into your equations. So these are the values or expressions we would plug into our equations. And if you plug in a positive when you should be plugging in a negative, the equation is going to give you the wrong answer. So it's really quite crucial to get this negative sign. And remember, one good way to do that is, two good ways are, first, figure out the signs before you do the magnitudes so that you don't forget about the sign. And secondly, always include a plus sign in front of your positive components, and then you'll probably remember to put the negative sign in front of negative components. Now, for all these problems, I've been writing out every single step. Do you really need to write down every single step like this? Well, depends on how hard or how easy these problems are for you. If you're at the point where these problems are starting to get boringly easy for you and you always get them correct, then you can start to skip some of these steps. On the other hand, if these problems are still challenging for you and if you sometimes make mistakes, then it's important to write down every step until you get to the point when you're not making mistakes anymore. These problems are supposed to be boringly easy. This is not supposed to be the hard part of physics. If you're not at the point yet where these are boringly easy, you need to do more practice where you write down every single step until you get to the point where these are so easy, they're boring. So if you're finding this to be a boring video, that's great. It's supposed to be boring. You want to get to the point where these skills are boringly easy. Don't remember if I mentioned this yet, but let me just emphasize that there's a difference in our notation for the overall vector and for the components. Notice that for the overall vector, we use this symbol V to stand for the magnitude, whereas for the components, we use these absolute value symbols to stand for the magnitudes. This is consistent with what I think you'll see in your textbooks. In particular, you'll see this symbol used for the magnitude of an overall vector in your textbook. Now, you might also see this symbol. Another symbol for magnitude is this. Sometimes your textbook might use an absolute value signs to indicate a magnitude, or they might do this with kind of doubled up absolute values. So those all mean magnitude. This means magnitude. This means magnitude, or sometimes you might see this symbol that means magnitude. But the simplest symbol, obviously, to use is this, and this is certainly something you'll see in your textbook a lot. But for the components, a lot of textbooks don't use separate symbols for the magnitudes of the components, but I think these are good symbols for the magnitudes of the components. And we've seen it's useful for a beginner to have separate symbols for the magnitudes of the components because that's what you're actually finding when you use SOHCAHTOA, the magnitude of the components. Remember that on most problems, you wouldn't figure out every single one of these notations. But we're doing all these notations for each of these problems just to get practice with the notation and to get comfortable with the distinction between overall vector and the components. These are the notations for the overall vector. These are the notations for the components. Do you see why the components are in a way more useful than the overall vector? Why are the components more useful than the overall vector? One reason is that they're easier to plug into equations. It's pretty obvious how we could plug this mathematical expression into an equation, or this mathematical expression into an equation, but how could you plug this into an equation? It's hard to plug this into an equation because there's a bunch of words, like in this description. Our description of the overall vector tends to include words or angles that are difficult to plug into an equation. The components are much easier to plug into equations because they're just numbers or symbols, sometimes with the plus and with the plus or the minus to represent the direction. So it's a lot easier to plug a direction in terms of minus and plus into your equation than a direction in terms of an angle and words. That's one of the reasons and the advantages of breaking things into components. Please pause the video and try this problem. Now, this is pretty similar to the previous question, just extra practice. So for the magnitude here again, we'll just use the symbol F. We can't be any more specific than F as the symbol for our magnitude. And we can just use this picture right here. As the vector arrow. So the direction is and an angle of theta as shown. And again, this is meaningless unless you also include the picture, because otherwise we don't know where the angle of theta is with the horizontal or the vertical, say. And then we can just say that this has a magnitude capital F at an angle theta. All right, now it's time for the components. So we already have a line here that's parallel to the y-axis. So through here, I'm going to draw the line that's parallel to the x-axis. And where they intersect defines our right triangle. Of course, if you wanted to, you could also draw a right triangle above the vector, but that doesn't directly include the angle we were given, so that's a less conventional way to do it. All right, now the overall vector points down and to the right, so our components should point down and to the right. Or you can say this is the tail of the overall vector, so it should be the tail of the component. And this is the head of the overall vector, so it should be the head of the component. Anything I'm missing? Well, there's a big thing. We have to label the components. It's always really important to label each part of your picture. Here's our x component. Here's our y component. Okay, are we ready for SOHCAHTOA now? No, we're not ready, because remember we do the signs first. This is net to the left, which is our negative direction, and this is down, which is another negative direction. Now we can label hypotenuse. Now the vertical side is adjacent to theta, and the horizontal side is opposite to theta. I'll put in the asterisk to show that theta is the angle that we're focusing on. So we have sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. The opposite side here is fx, but as usual we want a length, so we're going to treat that as a magnitude in absolute values. And the hypotenuse, the length of the hypotenuse is f without the arrow, because this does not reflect the direction, it's just the magnitude. So here I use f without the arrow. And over here, similarly, cosine theta, the adjacent side is the magnitude of fy over the hypotenuse f. All right, and then we can multiply both sides by f. Oops, I forgot to put in the theta here. So that the f's will cancel. And we do similar algebra over here. So are these the components? No. These are the magnitudes of the components. The components include signs, a negative sign for fx and a negative sign for fy. So this is the most important thing we were trying to figure out on this problem. So then we have our x component and our y component, both negative. The direction of this component is left, and the direction of this component is down, as reflected in their negative signs. So this would be represented by a downward arrow, like in the triangle. And this would be represented by a leftward arrow. Oops, looks like I got them confused, didn't I? The x component is the leftward arrow, because x is our horizontal direction, and the downward arrow represents Fy. It's supposed to be straight down, as much as I can draw it that way. Then this magnitude is F sine theta. I don't include a plus sign because magnitudes are always positive, so there's no point including a plus sign on a magnitude. So this is another example of how to break a vector into components when you have no numbers, only symbols. I hope that was boringly easy for you. The most important thing, one important thing, is make sure you got these negative signs. So let's try a quiz question. Pause the video and decide if this is true or false. We actually talked about this before, but I wanted to emphasize it. This is false. This example we just did is a counterexample. In the example we just did, we used cosine for the y component, not the x, and we used sine for the x component, not the y. So why would anyone think this? Well, as I discussed earlier, even though this is not true in general, it's usually true. This is usually true. It's usually true that we attack things this way. Usually we do use cosine for x, and usually we do use sine for y, like we did in the previous problem. Most problems are like this, where we use cosine for x and sine for y. You just can't assume that it's always true. Why were these two problems different? Well, it's because this problem we were using an angle with the vertical. And this problem we were using an angle with the horizontal. But rather than trying to memorize that as a way of figuring out what to do, instead, how would you reword this so it is true? Well, as we discussed before, the one thing that's always true is you use cosine to find the adjacent component, and sine to find the opposite component based on the angle that you're focusing on. That's why we put in the asterisk so we know which angle we're focusing on. Why do we say we're focusing on theta? Because that's who we're taking the sine and cosine of. So the safest thing is don't be on autopilot. Don't try to memorize anything more general than use cosine for the adjacent component and sine for the opposite component. Okay, so here's our answer. By the way, I think I mentioned this, but this process we're using is called breaking a vector into components. What we did here was we broke F into components. And you can see you can break a vector into components even if you don't have any numbers for the vector. Please pause the video and try this problem. I think first here I'll actually draw the V arrow. So they told us that this was pointing left. So I want to draw a straight horizontal line to the left. That's the overall vector. And the direction is as they told us, left. And the magnitude is 8 meters per second. So then the overall vector would be 8 meters per second left. Remember that the arrow indicates the full specification of the overall vector, both the magnitude and the direction. On the other hand, this symbol means just the direction, and this symbol means just the magnitude. Without the arrow, it just means the magnitude. It's the same symbol you'll see in your textbook, although they might not talk too much about how that's what they're using that symbol to mean. Okay, so now how do we break this into components? I think I already talked about vectors which are parallel or anti-parallel to the axes before. Since this is anti-parallel to the x-axis, the y component is 0, which means there's no y component, no direction, no arrow, or you could say the component is 0. The y component is 0, which means it has no direction, and 0 vectors have no arrow. And then the x component, well, remember, do the sign first. This is pointing in our leftward direction, so the sign is negative. And then the magnitude of the component is just the complete magnitude of the vector, 8 meters per second. So here's the most important thing right here. If you got this whole problem right, but you left out the negative sign, then you really got the whole problem wrong, because the most important thing here is to get that sign correct. Remember, this is the number you're going to be plugging into your equations. And if you plug a positive number rather than a negative number into your equations will think that the vector is pointing to the right instead of to the left, and they'll give you the wrong answer. So remember, figure out the sign first, because that's otherwise something you're likely to forget. And if you put a positive sign in front of positive components, you're more likely to remember the negative sign in front of negative components. So the arrow that represents the x component is really exactly the same as the overall vector in this case. The component arrow is the same as the overall arrow. And the magnitude here is just 8 meters per second without the sign. Okay, so it's actually not too uncommon that you might see a vector that has only one component. If a vector is parallel or anti-parallel to one of the axes, then the other component is 0, and the entire magnitude goes into the remaining component. And the trickiest part about this is that students often forget to put in the negative sign on the component. Notice we don't put a negative sign here. When you use this notation, you don't represent the direction with a plus or a minus. You represent it with a word or an angle, like left or right. It's only when you're doing the components. That you represent the directions with a plus or a minus. So again, compare. In this notation for the overall vector, the direction is not represented by a minus. It's represented by the word left, or in a more complicated case, by an angle. We only use plus and minus signs for directions for the components. All right, please pause the video and try this problem. Well, we were given the F arrow. The F arrow is pointing straight down. It's supposed to be a vertical line, straight down. Hard to draw straight down. All right, now we'll just say the magnitude is F. So the direction is down. In this case, the direction was given to us implicitly by the arrow, rather than being given in words, but we know that direction is down. So we can say the overall vector has a magnitude of F, and that it's down. Now, since this is anti-parallel to the y-axis, the x component is 0. So there's no x direction and no x arrow. And the y arrow is the same exact arrow as for the overall vector, down. But remember, when we use the arrow notation, we describe the direction with the word down, or an angle. But for the component, we use a sign to indicate the direction. That's a big difference between this notation with the arrow and this notation for the component. So this is pointing down, which is our negative direction. So this component is negative, and we're using the symbol F without the arrow to stand for the magnitude. So the entire magnitude goes into the F component. Okay, so there we go, and we've broken this vector into components. Remember that if you left out this negative sign, you got the problem completely wrong, because this is one of the most important parts of the problem to get right. And this is what we're going to be plugging into the equation. The equation will give us the wrong answer if we don't plug in the negative sign. So we've learned how to break a vector into components when one of the components is 0. Please try this problem. Now, is this the same problem as the previous? Well, it does have the exact same vector, but it's not the same problem because we have different axes. And remember that components are a way of measuring a vector relative to axes. So if we change the axes, we change the components, even if it's the same vector. That being said, this should have been a real easy question for you. I hope this was boringly easy. Let's go through it. Well, we're not given any numbers for this vector, so as previously, we can just say that the magnitude of the vector will simply be symbolized by the symbol capital F. And we can see here that the direction of this vector is down, so we'll draw a downwards arrow. This symbol with the arrow requires a complete description of the vector, magnitude and direction. So do you see, so far, everything we filled out here has been exactly the same as on the previous problem, because here we're just describing the overall vector, and this problem had the exact same overall vector as the previous problem. But the components will be different because the axes are different. Now the x component will still be 0. Since this vector is vertical, it has no horizontal component. No horizontal component. 0, I should say, horizontal component, no horizontal direction. All right, and here's the only slightly tricky part. So first, remember, it's always good that the component should include a plus or minus sign, and you should put the plus or minus sign in first before you put in the magnitude, so you don't forget the sign. Well, the vector is pointing down, and on this problem, we've chosen down as our positive direction. So in this case, the vertical component will be positive. And then the magnitude of the vector, the magnitude of the y component will be the same as the magnitude of this vector, of the overall vector. The entire magnitude of the overall vector goes into the vertical component because the vector is vertical. All right, so the one tricky thing here is I do recommend that you include this plus sign. Remember, it's a good idea to include a plus sign in front of positive components so that you remember to put a negative sign in front of negative components, and also because the plus sign reminds you there's an important meaning to this being positive. The meaning is that this points in the positive direction, which in this case is down. The y component points in the same direction as the overall vector here, which is down. The magnitude of the y component is the magnitude of the overall vector, f. Here we don't include a plus because magnitudes would never be negative. So we don't need to emphasize that it's positive. Remember that concepts which could never be negative, you don't need to emphasize that they're positive with a plus sign. So I don't need a plus sign here or here, because those magnitudes would never be negative. But a component could be negative or positive, theoretically. So when it's positive, you should emphasize that with a plus sign. Those are good notational habits for a beginning physics student. Now, most of the problems that you do, you will usually choose up to be your positive direction. But every once in a while, you probably will see unusual axes. Every once in a while, it'll be convenient perhaps to choose down as your positive direction. So remember, don't be on autopilot when you're breaking vectors into components. Always pay attention to the actual axes that are being used. If down is our positive direction, then a vector that points down has a positive y component. So you can compare our answer here and our answer here from the previous example to see what happens when you keep the same vector but change the axes. When we keep the same vector but change the axes, nothing about the overall vector changes, but the components change. In particular, in this case, since we shifted from up being positive to down being positive, the y component shifted from being negative over here to positive over here. Even though it was the same vector in both cases, the components were different because the axes were different. So remember, always write down your axes when you're doing these problems. All right, I hope that was a very easy example for you. The lesson is always write down your axes and pay careful attention to the axes when you're breaking vectors into components. Components are a way of measuring vectors relative to the particular axes that you choose for that particular problem. And again, I encourage you to put a plus sign in front of positive components so that you'll remember when it's necessary to put a negative sign in front of negative components. Try this problem. Well, this one should have been extremely easy. I'm just going through this for completeness. We know the vector has a magnitude of 0. So we can start by filling in this symbol, because remember this symbol without the arrow stands for the magnitude, and we know that magnitude is 0. Now, 0 vectors have no direction. 0 vectors have no direction, and therefore they have no arrow, because an arrow would show the direction. Also, they can't have an arrow because remember the length of the arrow is supposed to represent the magnitude. So to represent a magnitude of 0, you would need an arrow with 0 length, which is another way of saying no arrow at all. Now remember, this symbol with the arrow stands for the complete description of the vector, magnitude and direction. So we can say, to describe it completely, that it has a magnitude of 0 and no direction. Any vector with a magnitude of 0 has no direction. And then it should be very easy to break this into components. Since the overall magnitude is 0, each of the components is 0. And again, there's no directions for those components. There is a magnitude, so to speak. That magnitude is 0. Okay, well, that should have been extremely easy to fill out. I just wanted to go through this easy example for completeness, but this is certainly relevant for solving problems because you will occasionally be working on a problem where a vector has a magnitude of 0, and you need to plug in those components of 0 into the problem. So you will see examples, for example, where acceleration has a magnitude of 0, and then each of the components is 0. The acceleration will be 0 on a problem where an object is moving with constant speed, for example, or an example where an object is motionless. Those would both be cases where the acceleration would be 0, and therefore you'd plug in 0 for each of the components. Here that a 0 vector has no direction and therefore is not represented by an arrow. And a 0 component has no direction and would not be represented by an arrow. In this video, we have discussed how to break an overall vector into its components. But keep in mind that this is a multiple video series with a number of videos in the series. So I hope that when you're ready, you will proceed on to the next video in the series. So that you can continue to develop your skills for working with vector components. And of course, keep in mind that all the problems that are discussed in this video series are contained in the problems document, and there are solutions in the solutions document. So if you're feeling that the videos are moving too slowly, or if you want to see what types of topics are covered in the later videos in this series, you can always just go ahead and start trying the problems in the problems document and checking your solutions in the solutions document, and perhaps just skipping to particular parts of the videos that deal with topics that are not clear to you from the solutions. But of course, if you find this material in general to be difficult and challenging, then you can simply continue to watch each of the succeeding videos. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.